Hello everyone, and welcome to our second lecture on op amps. In this lecture we're going to be covering several different configurations with our op amps. So let's get started. Our first configuration here is going to be looking for Zn. Zn meaning what is our total impedance, which is also referred to as resistance. But what is our total impedance looking into our op amp? Okay, so we're trying to figure out what is our total impedance looking into our op amp. Okay, we have a configuration here, so we can see that it is open loop gain, meaning that we have no feedback coming out of our output back into our input. So, but keeping that in mind, even though we know that our open loop gain is 200,000 without basically when it's open loop, we are not going to be considering that in this scenario. So we're just going to be looking for what kind of output we're going to have based on what's coming in without consideration to our open loop gain. So it's all about just calculations. We're just looking for numbers based on the input and the output. First thing we need to do is look at our configuration. We see that we have at VCC, we have 12 volts here, and we have VEE, which is on the negative supply of 12 volts as well. Now, if we look at our circuit here, we see that we have a potentiometer right here in the middle. So, and everybody should know what a potentiometer is. In this case right here, we have what we call a voltage divider network, because this right here is nothing but a potentiometer with a center tap in the middle of it. So in other words, basically what we have is we have a upper resistance here from this center tap and a lower resistance from the center tap. That's where we get our voltage divider network from. Okay, so now that you understand we have a voltage divider network in this circuit, the next thing we need to do is we need to go ahead and we can calculate what our total current is based on our voltage and our total resistance. So our total resistance for our potentiometer is 200K. So that means that we know that current is flowing from negative to positive. So our current flow is like this way, coming up through here and back up to our 12 volts. So as you can tell, current is flowing through the entire potentiometer resistance. So now we can calculate what our current is through this whole thing. So Ohm's law states that I equals E over R. So if we take our voltage, which is 12 volts, and place it into our formula right here, and our resistance, which is R1, and you can see R1 up here refers to the potentiometer. If we divide those two, we come up with 60 microamps. This is our total current running through that leg. Okay, so keep that in mind. Now we have total current running through that leg. And so now we can start to calculate our voltage drops. So I've already given you the values of the adjustment of the potentiometer. So at point B right here and at ground, which is right here, I have given you a value. I've adjusted this to a value of 45 k ohms. All right, 45 k ohms. And that, of course, would mean that the rest of this resistance from this point right here and upward would be 155K. Okay, because that would be the rest of the 200K. So I've given you that value. It's just a random value, a random adjustment. So we have 45K at that point at point B and with reference to ground. So now we're looking for the voltage drop. Let's see, the voltage drop for VZN. So in this case right here, we have our voltage, we have our current, which is 60 microamps, okay, and we have our 45 ohms of resistance right here on our pot. So V out at that point is going to be IT, which is our total current, times that 45K, which is our 45K, which is going to give us at that point a negative, or let's just say 2.7 volts. It's not negative yet, but this is V out. And the reason that this is negative at V out is because at this point right here, we have that 2.7 volts felt on this leg, which is our inverting leg. Okay, so if we have 2.7 volts here, it's inverted, and on the output, we get a negative 2.7 volts. So that's where that comes in. Now, how do we figure out what is the value? Get it out of this. How do we figure out what the value is at VR1 at this point? So that's pretty easy. We have our VCC, and we've calculated for our VZ in, which is also basically our V out minus the, without the negative yet, which is 2.7 volts. So we subtract the difference and we come up with our 9.3 volts. And if you add those together, you come up with our total voltage drop of 12. So in this case right here, we have our total voltage, everything adds up, and we have a negative 2.7 volts on our output now. All right, let's see. Okay, so that is our first example here. Now let's say, get out of this real quick. Let's say I adjust the potentiometer to 75 k ohms with respect to ground. Okay, this is with respect to ground. In other words, at this point here and this point here, which is respect to ground, I've adjusted it to 75 k ohms. So in this case, ignoring the open loop gain again, what would be our V out? So we've already calculated for total current. That does not change because we did not change the size of the pot, which is 200K. So we still have the 60 microamps, and then, but now we have a 75K adjustment, and if we multiply those together, our V out, or actually our VZ in this case, is going to be 4.5 volts, and it is also on the inverting leg. So this is how we're going to come up with, after it's inverted on the output, we're going to get that negative 4.5 volts. All right, so that's a couple examples for trying to find Zn. So this whole thing is about trying to find Zn. And so now that we have our voltages on those couple examples for our V out, hold on. All right, so now we can apply our values to to Zn, which is right here. In this case right here, our first example for VZN was just the 2.7 volts. We would multiply that times R1, which in this case is the entire 200K, and then we would divide that by what voltage we had on VR1, which was up here, which was the 9.3 volts. If we plug those into our formula, we get a Zn of 58 k ohms. This is the impedance that the op amp sees coming into the op amp itself. So that's how much resistance our op amp actually feels on the input. And that is how we calculate for Zn. All right, any questions, just please let me know, and I'd be more than happy to help out. All right, so that takes care of VZN. Now let's look at finding Z out. All right, in this case right here, let's start off. This one's a little simpler. Our formula for Z out is VDiff, okay, times RL, which is our load. In this case right here, we're doing 400 ohms, divided by VRL, what our voltage would be across our load. So how do we come up with this negative 12 volts for VRL? Well, that's pretty simple. We just look at where the voltage is coming from. In this case, our voltage is coming from this positive 12 volts on VCC, which is felt down here on the inverting input. So if it's positive coming in, then we're going to get this negative 12 volts coming out. Now keep in mind that we've looked at the, on your PowerPoint, you saw that we had an ideal op amp and a typical op amp. And I gave you some values there for typical op amps, and realistically, we're going to have a 1 or 2 volt drop from the internal resistance of the op amp itself. So theoretically, it wouldn't be a complete negative 12 volts, but it would be somewhere around 10 or 11 or something like that. So, but just for calculation purposes, we're just keeping it as just coming out the exact same amount. Okay, so we're trying to find Z out. So we need the difference in the voltage. And let me back out of this real quick. Okay, so we need the difference. We need the difference in the voltage. So in this case right here, I don't have any kind of voltages on here. So I gave you a random value of 2.4 volts for VDIF, just so we can do this based on calculation purposes only. So now we can calculate what our total Z out would be. So if we plug in the values of RL, which is 400, and we plug in the it doesn't matter if you plug in the negative or just the 12 volts, positive 12 volts. We're still looking for Z out, which is impedance, in other words, resistance. If we plug those into our formula here, we will come up with a value of 80 ohms. In this case, if you did negative here, then it would be a negative 80 ohms, but resistance is resistance, so we're not really worried about polarities as far as that's concerned. But that's how we would come up with our Z out based on this configuration. All right, let's see, what else? Okay, so now I've given you a different scenario here. We're looking to find the difference, or VDIF, based on Z out being 25 ohms. This is just a random number that I've given you. But how do we calculate to find VDIF? So basically all we would do is rearrange our formula. We would pull out VDIF, and then we would come out with this formula right here to find the value. So if we plug those values into our formula here, you'll notice that our VDIF would come out to be 750 millivolts. Now remember, that means that it's coming into our op amp here, and right now it's showing this is what VDIF looks like, because VDIF is on this side of our op amp and it has not been inverted yet. So your actual output on this right here would be a negative 750 millivolts if we were to calculate that. Okay, so that is how we decide. That is how we determine trying to find VDIF if Z out was given. All right. If you have any questions, please let me know. All right. Our next one. Let's see. All right. In this one, okay. So here we're looking for basically the voltages on the output, okay, and the polarities. So you've seen this before, all right, our VDIF, basically our difference in voltage on V1 and V2. So V1 still same formula, V1 minus V2. And so now we need to look at our configuration of the circuit. So in this case right here, let's start off with the easy one, the easy part of this circuit. Here we have, in this case, we have a nice simple voltage divider network. In this case, we have, instead of a potentiometer, we have two resistors in series with each other. So how do we come up with this 6 volts right here at this point, which is coming into our inverting side? So how do we come up with that? Well, it's pretty simple. Using Ohm's law, well, let's look at current flow first. So current flows from negative to positive, so we have current flowing this way, back up to our positive 12 volts, And now we know where this comes from. If both of these resistors are exactly the same value, we automatically can say that each one has 6 volts across them. So if that's the case, we have our 6 volts right here in the center. So no calculations needed for this, pretty straightforward. So we have 6 volts sitting on our inverting input. All right, that was pretty straightforward, easy. And so now, let's take a look at this leg right here. This is the most important leg. First thing we need to do is, what do we need to do first here is calculate what is our total current running through this leg. Okay, forgetting that we have a pot right here for a second. We know that that is also a voltage divider network as seen earlier. But now we need to determine total current. So in this case, we have current flow this way, all the way back up to our 12 volts. So if we look at this current flow, the direction of it and everything, we can see that we have 2 resistors in series with each other going up to our 12 volts. And that is these 2 right here. So to figure out total current, we need to know total resistance, and in this case right here, we have a total resistance of 20,100 ohms. We have VCC of 12 volts, so basically what happens is we have our 12 volts here, we added up both of these here, and our total current came out to be 597 microamps. So now we have our total current for that part of the circuit. So 597 microamps. Okay, now that we have that, we're still working on trying to determine what V out is going to be when we get here. So remember, keep in mind that at this point right here, we have that 6 volts. Okay, so we need to find out what is coming in here at this point, because we have to find out what the difference of those two are. So here we have at VA, excuse me. All right, if we, let's see, where did I adjust this here? Okay. All right, so if we have this adjusted, I got this here, if we have this adjusted, if minimum from point A, okay, to ground, then the input would be very minimal. Meaning, get this highlighted here, meaning that if this is all the way, if this pot is adjusted all the way down to this point right here, okay, all this line is feeling right here is what's coming across this resistor. Okay, this is the very minimal, because this is not a potentiometer, it is a fixed resistor, a fixed value. So that means current is just flowing through this resistor here and then this way. All right, so we have total current. So if we take that total current and multiply it times this 100 ohms, there are R4, which is this part, okay, it's going to give us 59.7 millivolts at this point right here. Okay, it's getting a little confusing here, but let me back out of this. So we know now what we have at the non-inverting leg coming into our op amp. So let me back out a little bit here. Okay, so now that we have this value here at this point right here, non-inverting, now we need to be able to, all we have to do here to figure out what V out is find the difference between these two. If we have 6 volts at this point and this 59.97 millivolts at this point, we subtract the difference, and V out is going to come at this point right here of a negative 5.94 volts, because this 6 volts here is larger than this 59.7 millivolts. So the difference would be 5.94 since it's positive right here at this point. And since we're going through the inverting leg, that's how we come out with negative 5.94 volts on the output. All right, let's look at one more thing here. Okay, so how do we make, one of the things that we want to do is we need to figure out, especially if this is a circuit that's going to be a sensor type circuit, all right, that might break like a security system or something. we want to try to keep this point right here at 0 volts as best we can. So that if something changes on our input, then we'll be able to know if that circuit has been triggered. Okay, so how do we do that? How do we figure out how to get this point right here to equal 0 volts based on the same circuit? So what we need to do is we need to figure out what we need to adjust R3 to with respect to ground in order for us to actually get 0 volts out. So the first thing that we need to do is, and this is where most students kind of stop, but we would think that since we have a voltage divider network here, okay, based on this point right here, the only one that's really a voltage divider is this one. So that's why we need to adjust R3 in order to try to get that 0 volts out. So if we just add these up and divide by 2, that's not going to work for us because we still have this 100 ohms that's down here on this bottom leg. So the way we do that is that we would take this, that's our first step, is add them both up and then divide by 2. So once we do that, then we're going to take this bottom leg that's right here, or this bottom resistance of 100 ohms, and we're going to subtract that from that value. And when we do that, we come up with this approximately equal to 9.95 k ohms that we adjust our pot to, our potentiometer. So in this case right here, we're going to adjust this potentiometer to 9.95 k with respect to ground. So once we do that, then this will be equal, this potentiometer will be equal based on having this 100 ohms at the bottom. So the resistance from, let me back out of this a little bit here. So the resistance from this point right here to this point right here is going to be the same as this point right here to this point right here. And that will give us that 6 volt drop as we have on the other voltage divider network that's in here. Okay, and then if we have, like I say, if we have that 6 volts here and that 6 volts here, those will cancel out with each other because they are with respect to ground on this V1, and that will give us a 0 volts on the output. Okay, similar to your lab 1, you were looking at different values on the legs, on the inputs, trying to determine what the output would be. Okay, if you have any questions, please just let me know. All right, moving along. Okay, so here we have a little bit different scenario. We're not going to worry about this one right now, but let's look at this one. So in this circuit right here, okay, we're going to be looking to find X of C, we're going to be looking to find Z, and then what is our total or our current for R1. All right, so this is a little bit, you should have had a little bit of this already in the past, but this X of C, let me back out here, this X of C is what we call the capacitive reactance. In other words, what is the resistance of this cap, this 49 microfarad cap in this circuit. This one's pretty straightforward. All we're doing is our formula is going to be based on the frequency and the capacitance. So 2 times pi times frequency, in this case right here, the frequency is 2k hertz, and then our capacitance here is 49. If we plug those values into our formula, we're going to come out with 1.62 ohms of resistance. Remember, capacitive reactance is rated in ohms. All right, the next thing we want to look at is what is Z, our total our impedance looking into this circuit. So straightforward, just following the steps as we go down. R squared, which is our 20k ohms right here, squared, plus X of C squared, which is our 1.62 ohms. And once we do that, since X of C is so small, it's not really going to give us much of a change from the 20k ohms on our R1. All right. Okay, so, all right, then we want to find out what our IRMS is. Okay, so if If for some reason it's given in 10 volts, in this case right here is 10 volts peak to peak, our voltage in RMS formula for the conversion would be that divided by the 2.828. And that will give us our 3.54 volts RMS. So in this case right here, we're trying to find out what IRMS is, or the current for that. So at VA, which in this case right here, which is our applied voltage, which was the 3.54 volts on the input, divided by our Z that we just calculated for, which is 20K, that is going to give us a current of 176.99 microamps. All right. Now, our V out, disregarding our V out right here, disregarding any open loop gain, because this is all open loop, there's no feedback again. What is going to be our output? So basically in this case right here, let me go back a little bit here. So our output is going to be whatever the input is coming in. So here we have, and don't forget that this is on the inverting leg. So if this signal starts off like this 10 volts peak to peak coming in, on the output, it's going to be like this. Okay, it's going to be inverted. That's all there is to it. And like I say, this is just, we're not worried about internal resistance or loss on the internal resistance of the op amp. So we come out with a value of negative, basically a negative 10 volts peak to peak. All right, if you have any questions on that, just let me know. All right, let's get out of this real quick. All right. Okay, so now we're going to be looking at finding slew rate. All right, so what is slew rate? Slew rate is basically what happens is that whatever frequency we have coming into our op amp, the op amp can only handle so much. In other words, if the frequency gets too high, then our output is going to start to attenuate. In other words, it's going to start to get smaller and smaller and smaller because the op amp can't keep up with the change that's coming in from the input. So our slew rate is going to be what we refer to as the volts per microsecond coming into our op amp. So that is our slew rate, and you'll get more information on that as we go. But anyway, and you'll see that in the labs as well. As you increase voltage, you'll see what happens on the output. All right, so what do we have here? So in this case right here, I've given you a value for V out based on the input. So our change in voltage from the V out, our V out now is going to be whatever V out is based on the input, is 24 volts peak to peak. So now that we have our 24 volts peak to peak, we can go ahead, and we don't really need that here. This was just a measured output, which I just made up. We can figure out now what our time is based on the frequency. So we know that this is the frequency coming in, the 20 kHz. How do we figure out what time is? We just reciprocate that, 1 over 20 kHz, and that's going to give us this value of 50 microseconds. Okay, now that we have our value of 50 microseconds, and we have our time, our change in time, and our change in voltage here, we can apply that to our formula for slew rate. So in this case right here, if we did this, basically what happens is that slew rate is going to equal, it's going to come up to 480K. Well, that's not how we write slew rate. Slew rate has to be based on the spec sheet, and I'll be sending you a spec sheet. It's based on a voltage per microsecond. So in order to write this correctly, we have to take that and multiply it times 1 microsecond. And when we do that, it's going to give us this 0.48. And since we multiply it times 1 microsecond, we can say that our value, our slew rate, is going to be 0.480 volts per microsecond. Another way you can do this is if we have 480, I'm going to say 1,000 here, 480,000, which is what this is. Since we're dividing it by microseconds, microseconds is 6 placeholders. So if we're right here, we can say 1, 2, 3, 4, 5, 6, and this will give us the same thing, 0.480. All right, that's how we come up with that. So now that we have, let me get out of this. Now that we have our slew rate based on these inputs or these values, we're going to say, how do we determine if this slew rate value right here is going to work for this op amp? So on the spec sheet, you would see that the average op amp has a rating of 0.5 volts per microsecond. So if it's less than 0.5 volts per microsecond, then whatever frequency is coming into this op amp should be able to have on the output without any attenuation, except for, of course, our loss in the internal resistance. We should have no attenuation. So how do we figure out what is the maximum frequency that we can put into our op amp? Well, in this case right here, our formula starts right here. Our formula starts right here. So it's for frequency max on the input, it's going to be our slew rate divided by 2 times pi times volts peak. So we need to make sure that when we put this into our calculator, that slew rate is going to be like this right here, the 0.5 volts, which is what our spec sheet says, per microseconds. Now, I just rearranged it a little bit here to give you better understanding, but this is how you would actually place this formula into your calculator. And when you do that, it's going to come up and it's going to tell you what the maximum frequency is. And in this case right here, let's see, all right, so let's put that into our calculator real quick here. We have 0.5 volts divided by 1 microsecond. All right, and then divided by 2 times pi times volts peak, which is in this case right here. It's 7 volts peak to peak, but we need peak, which is 3.5 times 3.5. Okay, and that's going to give us a value of a frequency of 22.74. So 22.74 kHz would basically be our maximum frequency before we start to attenuate the output. In other words, we should be safe in saying that we have, if we put a frequency of 22.74 kHz, we'll be okay on the output. We'll get the full range. So, with that being said, if for some reason I decide to increase this input frequency to 23 kHz and put that into our formula, we're going to see that this is going to come out to be 0.552 volts per microsecond, which in this case would start to attenuate. Because remember, the spec sheet tells us that our maximum volts per microsecond is 0.5 volts per microsecond. So keep that in mind. If we start to go over this 0.5, then we can start to see attenuation on the output. So you will see that. You will have examples in the classroom to actually see how this functions on your circuits when we start using the oscilloscope and the function generator. Okay, so that is our slew rate. And I just gave you another example here, the V out, if V out was 10 volts peak to peak. And then, let's see, we had a 20, let's see, I think that was 20 microseconds. Oh, I think I just gave you these values just for random values to find out what our slew rate would be. So if we take these values here and put it into our slew rate formula, we have 10 divided by 20 microseconds, and that would give us a value of the 0.5. Okay, so basically this was a scenario right here that we could use to reach our maximum input frequency. So that would give us the 0.5 that we would need. So if we wanted to find out what the frequency was, of course, we would just take this 20 microseconds here and then reciprocate that. Do 6, reciprocate, and that would give us a a 1.67 megahertz that we could put into this circuit and still maintain that the slew rate, without having attenuation on the output. Okay, all right. So we will do that in the lab. So just let me know if you have any questions. All right, so let's see. And that is it. So that is our circuits for this next lab that I'm going to be sending you guys. So if you have any questions regarding the labs or anything, please let me know, and I will be more than happy to help. All right, thanks guys.